So, welcome back, everyone. We will be starting our class. And am I audible? If I'm audible, please respond, one of you. And I want to know if you can see the PowerPoint, the screen I'm sharing. Can you see the PowerPoint, the slides I'm sharing with you? Can someone respond? Hello. Can someone respond me either in the chat or through your voice? I want to know if I'm audible and the screen is visible to you. Hello, everyone. Can you respond, anyone? Hello, can you hear me? Oh, so unfortunately, the waiting room was enabled. Yeah, unfortunately, the waiting room was enabled, so I was not at all aware of this. So I hope I'm audible and the screen is visible to you. By default, the waiting room was on. Yeah. So I guess I can start the class if I'm audible to everyone. Okay. So let me start the class. And please mute yourself also. Please mute yourself. Hello, am I audible?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
You can see the screen, right?
Yes, sir.
All right, we'll continue because otherwise we are already wasting a lot of time. Yeah, mute yourself, everyone now. If I'm audible, mute yourself. Roll number 230. You have to mute yourself. So type your attendance there. That will be automatically recorded as attendance for this class. So far what we have discussed was that we have discussed the concept of gradient, divergence, and curl. And we have also deduced certain interesting ideas about those divergence, curl, and gradient, what they are physically, what they physically means. And we said that gradient defines the direction in which there is a maximum change in that scalar function. And gradient of any scalar quantity is a vector, because we are having a vector del operator operating on a scalar quantity that results in a vector. And when we talk about divergence, this is a divergence is del operator operating on a vector quantity, and that measures, that is a measure of the net outflow of a vector field, the net outflow of a particular vector field. So like we discussed in the case of charged particle, electric field due to charged particle, there we see that there's a net outflow of electric field vector. Then we have their finite divergence. But when we talk about this curl only measures the rotation of the vector on which the del operator operates. So like in the case of magnetic field, the curl of a magnetic field is non-zero, as we already know in this Ampere's law. So that means there is a rotation of that magnetic field vector. There is a rotation of the magnetic field vector. That is, the magnetic field vectors are not straight lines. Okay, so that is what we have learned so far. Now, these are some of the simple examples on this gradient, divergence, and curl. And the solution is already given to you in your notes. You can see here that so some people are still joining, and unfortunately waiting room was enabled, and I have to keep monitoring the waiting room also. I hope everybody has joined. Now there are 66 of you. So here, as you see, you have this del operator operating on ln of magnitude of r vector. Then what is this quantity, magnitude ln of magnitude of r vector? Ln of magnitude of r vector will be scalar, isn't it? This will be a scalar quantity because we are considering the natural log of magnitude of your position vector. R vector, as you see, it is a position vector in a Cartesian coordinate system. So your R vector is x, that is the coordinate value along the x-axis, into I cap unit vector along the x-axis, plus y into j cap plus z into k cap. So this is a position vector. This defines, this R vector can be used to define any point in this three-dimensional Cartesian space. So any point in this three-dimensional Cartesian space, you can define the location of that point or the position of that point by identifying what is the corresponding value of x component of that location of the, what is the coordinate of that the coordinate value along the x, and what is the coordinate value along the y, and similarly the coordinate value along the z. Then by writing in this vector form, you can define the position of that particular point in this three-dimensional Cartesian space. Now, in order to take the magnitude of it, here usually when we are not writing, you need a vector sign on top of your position vector r. Simple r means it represents the magnitude of the vector r. Okay, we already know the vector r here. When you take the magnitude, you know that you have to take a square root, and then you take the square of all this x, y, and z. So square root of x square plus y square plus z square will be the magnitude of your position vector. And if you write in terms of this power, you can see that x square plus y square plus z square to the power whole quantity to the power half. That is your magnitude of the position vector. Then you can take the natural log on that. When you take the natural log on that, you know the logarithm, the natural log of any quantity having a certain power like this, x to the power a will be a into ln of x. So if you follow this, you can write this as 1 upon 2 of ln of x square plus y square plus z square. And here this is a gradient, as I already said. Gradient is a del operator operating on a scalar quantity. So as you see here, ln of magnitude of r vector is scalar. If you look at this quantity, the one I circle here, this is a scalar quantity because there are no vectors here, isn't it? Now, so when you have a del operator operating on the scalar quantity, this is simply del operator is I cap del upon del x plus j cap del upon del y plus k cap del upon del z operating on half of ln of x square plus y square plus z square. And here you see that when this operates on this, this being a scalar quantity, this scalar quantity has to be multiplied with each and every operator, spatial operator. Scalar quantity has to be multiplied with del upon del x, and it also has to be multiplied with del upon del y and del upon del z. As you can see, scalar quantity is differentiated with x, differentiated with y, partial differentiation with z also. And when you do the differentiation, I guess everybody knows how to differentiate ln of x. So you know that when you differentiate ln of x, del upon del x, for example, this is simply 1 upon x, right? So if you differentiate ln of function of x with respect to x, this will be 1 upon function of f of x, 1 upon f of x into differentiation of f of x. So this is simple calculus. So it's a differentiation of ln of function of x will be 1 upon function of x into differentiation of function of x. So if you perform that over here, as you can see, the function of x, y, z is this x squared plus y squared plus z squared. That will be, once you differentiate ln of that, it will be 1 upon x squared plus y squared plus z squared multiplied by differentiation of this function with respect to x. So when you differentiate x squared plus y squared plus z squared with respect to x, then definitely you will get 2x, isn't it? So differentiation of y squared with respect to x is 0, z squared with respect to y is 0. Differentiation of x squared with respect to x is 2x. So if you follow the similar calculation, this is what you will get. And once you combine this, you see that 2 and 2 will cancel out here, numerator and denominator in each and every term here. Then finally you will have x plus I plus yj plus zk, and this quantity, as you know, this is the position vector we already defined here, and this will be your r vector. And as you can see, your magnitude of, wait, there are already 4 people in the waiting room again. Okay, so if you look at this magnitude of r vector is x squared plus y squared plus z squared to the power 1 upon 2. So if you remove this 1 upon 2, means this is simply your r square. R square will be x squared plus y squared plus z square. So this is what we get, isn't it? So that is a very simple calculation. So I think most of you will understand the calculation just by looking at it also. But just in case if anyone has a lack of understanding there. Now, let us continue with another example. This is also a similar example, that is the gradient operation. As you can see, this is a del operator operating on 1 upon r. And as I already said, when you simply write r, r means magnitude of r vector. Okay, so r vector, the position vector, I already defined, and this is your magnitude of r vector. That is how we obtain. I already discussed that. And 1 upon r will be simply this quantity into this thing, x squared plus y squared plus z squared to the power minus of 1 upon 2. And when this del operator operates on this, you see that this 1 upon r again is, this quantity is again is a scalar quantity. So when this vector operator operates on a scalar quantity, that scalar quantity will be differentiated with respect to x, with respect to y, and with respect to z. So individually, like separately, it is differentiated with respect to x, y, and z. And this differentiation, as I said, this is x squared plus y squared, x squared plus y squared plus z squared to the power minus of 1 upon 2. So when you differentiate this function, you already know that, like, the differentiation is something like this. suppose I have f of x to the power 2, differentiate with respect to x. This will be 2 times f of x into differentiation of f of x with respect to x. So the similar thing only. So if you follow that differentiation, then this is what you will get. Okay, this is f of x 2 minus 1, sorry, 2 times f of x to the power 2 minus 1 into differentiation of f of x with respect to x. So if you follow the calculus, the differentiation we already studied there in class 12, this is what you will get. So you can work it out yourself at home. And this minus term you put in the denominator, that will be as shown here, x squared plus y squared plus z squared to the power 3 upon 2, and 2 and 2 here will cancel out in each and every term here. Then finally you will have minus of xi plus yj plus z cap in the numerator, and that is your minus of position vector r vector, and denominator is magnitude of r vector to the power 3. So because we know that our magnitude of r vector is half, so if you have a 3 upon 2 as the exponential or the power term here, that will be your magnitude of r vector to the power 3. Now this is our del operator. This is also known as a Laplacian operator. So as you can see, when you have one vector operator multiplied with another vector operator with this dot product, as I already discussed, this is also known as a scalar product. Why do we call this a scalar product? The result of this dot product between two vectors is always a scalar quantity. So as you see here, del operator is a vector operator, dot product with another del operator, another vector operator, it results in this scalar operator. So Laplacian operator, as you see here in the picture here, this is a scalar operator. So you see that I dot I is 1, I dot j is 0, I dot k is 0. So the result will be del square upon del x square plus del square upon del y square plus del square upon del z square, the scalar operator, right? So these are some examples on Laplacian operator. So again, your R here is your magnitude of your position vector that we already discussed, and del square is your scalar operator. So when the scalar operator operates on this scalar quantity, this scalar quantity, that is 1 upon R, will be will have to be multiplied with each and every term here, that is del square upon del x square will operate on this 1 upon R, and similarly del square upon del y square will operate on 1 upon R here, and similarly del square upon del z square. So when you follow your, again another student, so when you follow your calculus here, this is del square upon del x square is 2 times differentiation with respect to x. So you can do it separately. That is, you can first differentiate with respect to x like this. So when you do that, this function whole quantity to the power minus of 1 upon 2, differentiation will be minus of 1 upon 2 into this quantity to the power minus of 1 upon 2 minus 1 into differentiation of what is within this function with respect to x. So differentiation of this quantity x squared plus y squared plus z squared with respect to x will result in 2x there. Okay, so 2 and 2 cancels out. This is what you will get in the first differentiation. So when you are operating or differentiating 2 times, you have to again differentiate this quantity with respect to x like this. So when you do that, you just follow differentiation of product rule. Okay, differentiation of product rule. If you have two functions and you have to differentiate, like for example, if you have function of x, that is f, and gx, f of x and g of x, differentiate with respect to x, this will be f of x times differentiation of g of x with respect to dx plus g of x times differentiation of f of x upon dx. This is again your calculus from class 11 and 12. So if you follow that, over here your first function is considered as minus of x, your second function is x square plus y square plus z square whole quantity to the power minus of 3 upon 2. So you first differentiate your second function, you just put the first function f of x, that is minus of x here, and differentiating the second function, this is what you will get, because as you can see, differentiation of this quantity to the power minus of 3 upon 2 will be minus of 3 upon 2 into x square plus y square plus z square to the power minus of 3 upon 2 minus 1. Minus of 3 upon 2 minus 1 will be minus of 5 upon 2 as shown here. So again, differentiating what is within this bracket here of the function, that will be 2x, because differentiation of y square with respect to x and z square with respect to x will be 0. And for the second term, you have to consider this as your g of x. Yeah, another student has turned up. Yeah, so please mute, someone is okay. So your g of x will be this, and differentiation of minus of x will be simply minus 1. So if you follow that differentiation steps, you already know. So what I strongly suggest to every one of you here is that all these study materials are provided to you, and you already have the basic knowledge of differentiation and integration yourself. So you better work out all these mathematical steps, even though I've given you all the mathematical steps, but not without looking the mathematical steps given to you. If you work it out all these differentiation steps by yourself, that will help you in understanding, and also it will definitely help you in your calculation speed also, that is your knowledge on your calculus also. You can quickly finish all this kind of calculation through practice. So everything is there in your notes, so you have to practice with your notes. Now the next point is, yeah, if you continue that, you will get 0. The next point is to show that divergence of product of scalar and vector, divergence of phi and a vector is equal to gradient of phi dot a vector plus phi, the scalar quantity, into divergence of a vector. So this is a vector identity which you must memorize. This is a vector identity which you would come across very often in your further studies in physics, and also probably in certain like applications of other fields, also other fields of study like geology, and this maybe in mathematics also. So when you are dealing with vectors, you will often encounter this kind of vector problem, that is divergence of product of scalar into another vector. So this is the proof. The proof is given to you here, but you have to memorize this. You need this identity in many calculations. Okay, so as I said here, phi is your scalar, a is your vector here. So a as a vector function, sub phi is a scalar function. Phi scalar function means phi is depending on your position coordinates, that is x, y, and z. A as a vector function means a is also depending on your position vector, position coordinates, that is x, y, and z. So these a vector and phi scalar quantities, they vary with space. So you consider any point of space, this vector and the scalar functions, they will be varying with, they will vary from one point to another point. So when you express in terms of vector components, a1 is simply the component of a vector along x-axis, because this is the coefficient of your I cap unit vector along the x-axis. A2 again is the coefficient of your j cap unit vector along the y-axis. That means A2 is your component of the vector A along the y axis, and similarly a3 is a component of vector your a along the z axis. And here when I say that a as a function of x, y, and z, this component along the x axis a1 can be a function of x, y, and z, a2 can be a function of x, y, and z, and your a3 can also be a function of x, y, and z. So it is not mandatory that a1 is a function of all these x, y, and z quantities. It could be a function of x only, or it could be a function of y only, or it could be a function of z only, or it could be a function of two of these coordinates, or it could be a function of all these three coordinate values. Okay, so depending on the vector, the physical quantity this vector is representing, these components along the x, y, and z, they could be a function of any of these coordinate variables x, y, and z. Now when you have this divergence of product of scalar and a vector quantity like this, as you see, del operator, again a vector operator is I cap del upon del x plus j cap del upon del y k cap del upon del z. And so as I said at the beginning of this class also, whenever you have a dot product, never forget to write a dot here. Okay, so some students like they simply arbitrarily write dot and cross here and there. So but when you do that, it shows that you are lacking any understanding of this vector concept. So when there is a dot product, that means there is a scalar product between two vectors. So del operator is a del is a vector operator, and when vector operator operates on another vector quantity, there should always be either a scalar product sign, that is dot, or a vector product sign, that is a cross. Okay, so you cannot have del operator writing next to another vector quantity without those vector operation. Okay, you cannot simply write like that. But when you have one vector and another scalar quantity, never write dot nor cross, because dot and cross, they are relevant only between two vectors. So if you have one of them as a scalar, another as a vector, you simply write it like this. This is called gradient. Or you can simply write a vector into phi, that is a product of vector into scalar. So if you write dot or cross there, that shows that you are not having any understanding at all. So I think you will know what marks will be awarded to you. All right. So as I was saying here, this del operator is operating on these two quantities, the product of scalar and vector. So when you multiply a scalar with a vector, here the scalar quantity phi will be multiplied to every component of that vector. So the first component is a1 I cap, so you have to multiply the scalar with that component. And similarly a2 j cap, you have to multiply the scalar phi with that component. And similarly scalar phi will have to be multiplied with a3 k cap as shown here. All right, so this is a product of scalar and a vector quantity, a vector function. So this del operator operating on this product will be like this: I dot I cap will be 1, I dot j cap is 0, I dot k cap is 0. So therefore what you have finally is del upon del x operating on phi into a1, plus similar to what I discussed, j dot I is 0, j dot j is 1, we know that. So del upon del y operating on the product of phi into a2, del upon del z operating on the product of phi into a3. Right, so here finally phi is scalar, a1 is scalar, because a1 is simply magnitude of the component along the x-axis. So I cap is the unit vector along the x-axis. A1 is magnitude of the component of the vector A along the x-axis. So magnitude means A1 is a scalar. So here you have two scalar functions, phi and A1, and you are differentiating this true scalar function with x. Like I discussed before, you have to follow differentiation of product of two functions. So how is that? This is how we are doing. So you can take a1 as your first function, phi as your second function. You can reverse also, it will yield the same result only. So del phi upon del x into a1 plus phi into del a1 upon del x. This is what you will get when you differentiate a product of two functions. And similarly, this is what you will get when differentiating phi into a2, and similarly when differentiating phi into a3 with respect to z, this is what we get, right? So when you combine this term, and this term here, you will get this quantity. And when you combine phi into del a1 upon del x and phi into del a2 upon del y and phi into del a3 upon del z, this is what we have. And as you can see, phi is again scalar quantity. So phi you can take out of this, differentiation as a common term, right? So this will be, once you take out this, this will be I of del upon del x plus j upon del y plus k upon del z phi. And you can take, if you put a dot product here, you can write a1 I cap plus a2 j cap plus a3 k cap. So this quantity can be written like this. So this is same as this, because when you differentiate this phi, sorry, when you have this del operator operating on phi, this is what you will get. Let me write the intermediate step here. I cap into del phi upon del x plus j cap into del phi upon del y plus k capped into del phi upon del z. So this is what wait a minute. Yeah, this is what we will get when this del operator operates on scalar phi. We have already discussed that this is a gradient, right? So if you put a dot product here, there is a dot product here, dot product with your a1i plus a2j plus a3k vector. So this will result in I dot I is 1, I j dot j is 1, k dot k is 1. Then you will get this quantity just in the previous step. Okay, so similar to that, you can write this as phi into this quantity, as you can write it as phi into del operator operating on your a vector. So in doing that, you will arrive at this. So this quantity is grad phi dot with a vector plus phi into this del operator dot product with another vector. A will be divergence of your a vector. Del dot a vector is divergence of a vector. Okay, so that's how it is. And now let us quickly get into another identity. So this is another very simple identity which you always need to remember. That is, curl of a gradient of any scalar quantity is 0. That means gradient of a scalar function is irrotational. So I think this is quite obvious also, because if you remember what we discussed as the physical meaning of a gradient of a scalar quantity. So gradient of a scalar quantity, as we discussed before, it is representing the direction of maximum change of the scalar function. Gradient of this scalar quantity, it simply represents the direction of maximum change of the scalar function. How quickly the fastest direction, a particular direction in which you move your coordinate points, and your scalar function undergoes maximum change. So grad phi, as we discussed in the physical interpretation, physical meaning, it simply represents the direction in which there is a maximum change in that scalar function. So from that concept itself, you know that grad phi is simply certain particular direction. It's like as if it's a straight line, isn't it? So when you take a gradient of phi, as we discussed, curl of grad phi, curl measures rotation of the vector. So gradient of phi simply represents the direction of maximum change of the scalar function. So when you take the curl of that, it definitely is zero, isn't it? So if you remember the physical meaning or the physical interpretation of curl and the gradient, obviously you see that curl of a gradient of a scalar function is always zero. But you can prove it mathematically also, as you can see in the steps, because let me rephrase what I'm trying to convince you. Gradient of a scalar function, it simply represents the direction of maximum change of the scalar function. So it is a certain direction. It is not rotating, or it is not rotational at all, right? So when you take a curl of any vector quantity, will measure the rotation of that vector quantity. Gradient of phi is not rotating. It is simply a particular direction, a particular straight line or a particular direction. So gradient of curl of a gradient of a scalar function is always zero. So this is a vector quantity which you must again remember, and you will come across very often. And without having to do with this mathematical proof also, if you know the physical interpretation of curl and gradient, it is obviously zero, right? So phi is a scalar function. So gradient, when you take it, del operator operating on a scalar function, this is I del phi upon del x, z del phi upon del y. And when you take the curl of this, curl, if you remember the definition of curl, this is a del operator operating on this vector quantity. So you can write it in terms of this determinant, and that is I cap, j cap, k cap, and del upon del x, and similarly like this. So when you write in terms of this determinant format, you can take a determinant that is I cap into del upon del y operating on this del phi upon del z, del upon del minus del upon del z operating on del phi upon del y. So this is what you will get, plus j cap into this quantity and k cap into this quantity. So simply take the determinant of this, whatever I'm writing here, the determinant here. Now we know that like phi is a scalar function. Whether you first differentiate with respect to z and again differentiate with respect to y, or you differentiate with respect to y and again differentiate with respect to z, it will yield the same result only. Scalar function will yield the same result only. The order of differentiation does not matter at all. It will yield the same result only. Therefore, this term and this term will cancel out, and similarly this term and this term cancels out. Then what we finally get here in this mathematical verification is that curl of a gradient of phi is zero. Okay, curl of a gradient of phi is zero. Now, this is another vector identity which I will just quickly explain because we are running out of time. This again is another vector identity which you must remember. Okay, so this is a del operator dot with curl of vector A, divergence of curl of vector A, divergence of curl of vector A. So if you recall the physical interpretation of this divergence and curl, you definitely know that when curl of a vector A is non-zero, when curl is non-zero, that means the vector A is rotational. The vector A is rotational. So it's like the vector is moving around something like this. Okay, the vector A is rotational. So curl of A is non-zero means the vector A is rotational. If the vector A is rotational, there cannot be net outflow of the vector A. We know that divergence measures net outflow of the vector vector quantity. So when your curl of vector A is non-zero, your divergence will have to be definitely zero. If the vector A is rotational, there cannot be net outflow of the vector A. Therefore, divergence of curl of A is zero. Right. So from the physical meaning also, you can easily conclude that divergence of a curl of vector A is zero, which you can show it by this mathematical step. So again, you can write your A vector as this, and this your del operator. And when you take the curl of that, this is how we write using the vector product rule, cross product rule. That is the determinant here. You take the determinant, and this is what you get. And when you take the dot product with del dot product with the curl of A is this quantity. So del operator dot with this quantity will result in I dot I is 1, I dot j is 0, and so finally we will have del upon del x operating on this quantity plus del upon del y operating on this quantity plus del upon del z operating on this quantity. And when you differentiate that, this will be del square a3 upon del x del y and del square a2 upon del x del z. And finally, if you differentiate all this term, you will finally see that this quantity and this quantity will cancel out. This and this will cancel out, and this also cancels out. Therefore, divergence of a curl of a vector A is zero. Okay. So this is another vector identity which you have to do it yourself. You just consider a vector like this. A vector as a1 I cap plus a2 j cap plus a3 k cap, and you already know how to take the curl of A. So you take the curl of A, and again, instead of taking a divergence, you take another curl of that. Okay, so you work it out. This will be your assignment, and this assignment you try to work it out. I will give some more assignment also, so together they will amount to your internal marks also. So with this, I will conclude today's lecture. So if you have typed your attendance in the chat box, you can exit the meeting, and I will upload the lecture video again. Okay, thank you everyone for attending the class. Once you type your roll number in full, you can exit the meeting. So I hope everyone has typed their attendance, your attendance. So I'm ending the meeting. End meeting for all. So attendance, all attendances are recorded, I hope. For some reason.